friction. It is basically a force between two surfaces that are sliding or trying to slide across each other. A best example for that is when you're trying to push a book along the floor, friction makes it difficult. In the adjacent figure, you can see that this is the ground surface. There is some body or some block, you can say, which is in the blue color. The weight of this block is acting in the downward direction, that is the normal force. We are applying a force in the right side direction, trying to move the block in the right side, but there is some force which is acting in the opposite direction to the applied force, and that is called the frictional force. Friction always works in direction opposite to the direction in which the object is moving or trying to move. Another example of this is when you are skating or when you are driving. There is another force which is coming in the upward direction towards the direction opposite to the direction of your movement. That is the frictional force. Let us move ahead to the further topic or depth of this topic, that is what is belt friction. Now this earlier part of the video what I had explained was the generalized definition for friction. We are going to focus on belt friction since our practical today is associated with belt friction. So what is belt friction? It is a term describing the frictional forces between a belt and a surface such as a belt wrapped around a bollard. You can see here this whole region you can call as bollard, or you can call this small bollard is basically a hook kind of arrangement around which the belt is revolved or wrapped. When one end of the belt is being pulled, only part of this force is transmitted to the other end wrapped about a surface. The frictional force increases with amount of wrap about a surface and makes it to the tension in the belt can be different at both the ends of the belt. In simple words, I would like to explain. This is a pulley arrangement which you can see here, and the belt keeps rotating around. So the friction between this surface and the belt will be the belt friction. Now there will be tension in these two limbs of the belts. You can see here. This tension in both the belts can be different. So it depends. As we will move ahead, we will see the discussion. You will understand this concept better. Now, application of belt friction. Where is it applied? You can see there is some pulley arrangement here. Band brakes are there. A capstan is there. Use less smaller force to hold. Another is torque transmission. These are the basic applications where we will be needing belt frictions in our life ahead, or on application basis where we are going to require this. Now getting back to the details, we are moving to the analysis part now. So we will start a flat massless belt passing over a cylindrical surface. So this is a cylindrical surface. To understand the concept, I am giving this example. This is a cylindrical surface and there is a belt which is kept over it. If we have an equal tension in each belt, the belt will experience a non-uniform normal force from the cylinder, that is the support. So here T1 is equal to T2, and hence we can see that there is a non-uniform force which can be seen all over. With equal tensions on each side of the belt, only a non-uniform normal force exists between the belt and the surface. So if both the tensions are same, non-uniform normal force exists. What is the other case? If either of them is greater and smaller. So in a frictionless scenario, now we are assuming that there is no friction. If we were to increase the tension on one side of the rope, it would begin to slide across the cylinder. If I am going to increase this side, then obviously the belt will be moving in the right side direction, it will fall here. So in that case, the friction should act here, but we are considering that it is a frictionless scenario. If friction exists between the rope and the surface through, see, when there was no friction between the belt and the cylindrical body, the belt would just slide over with the weight. But if friction exists between the belt and the cylindrical body, then there will be some frictional force resisting in the opposite direction to that of the movement of the belt. With unequal tensions, a friction force will also be present opposing the relative sliding of the belt to the surface. This is what I explained in the previous statement. Now today's practical, what we are going to observe is going to be about the flat belt and the V-belt. So what are these two belts? A flat belt is a system where the pulley or the surface only interacts with the bottom surface of the belt cable. There is some flat kind of belt which is kept on flat surface of the cylinder, so that is flat belt pulley. So in that case, the belt which will be used will be the flat belt. If the belt or cable instead fits into the groove will be something like this shown in the figure. We are seeing the side view so that we can see the groove properly. Then it is considered as a V-belt. So it is along the depth. This is the first surface, it is along the depth, and then there is another surface of the cylinder. For a flat belt or cable will interact with the bottom surface. This is to be noted. In case of flat belt, the bottom surface is one which will be reacting. In case of the V belt, the belt or the cable will interact with the sides of the groove. So the friction here will be between the surface of the cylinder and the belt. In this case, it will be on the side surfaces of this groove and the belt. Now, what is the scenario in friction for flat belt? Somewhat this is an arrangement. This is a cylinder and there is a rope. It is the same arrangement. Just for explanation or for understanding the concept, I have turned the figure aside or rotated it with 90 degrees so that you can understand it better. So T1 and T2 are different tension forces acting here, and the formula for it is given by T2 maximum, that is maximum force at T2 will be equivalent to T1 e raised to mu s into beta. Now what is this mu s? It is the coefficient of friction between the surface and the belt. This is what we have to determine in this practical. The E part stands here for the Euler's constant, and beta is the angle of contact in radians. This is the angle of contact. Angle of contact of what? The belt and the cylinder. The maximum value of T2 before the belt starts slipping can be determined with the above equation. So we can determine the maximum value of T2 based on this equation. Now some theory about the same figure. When analyzing systems with belt, we are usually interested in the range of values for tension forces where the belt will not slip relative to the surface. Starting with a smaller tension force on one side, that is T1 on one of the side of the cylinder, we can increase the second tension force to some amount before slipping. So what is explained in this statement is, we can apply some load at T1 before the belt and we can apply some load at T2. Before the belt slips on either of the side, we can increase or add some of the weight onto the T2 side. For a flat belt, the maximum value of T2 will depend on the value of T1. So be careful that for a flat belt, the maximum value of T2, that is the second or the larger tension force, will depend always on the smaller tension force. The static coefficient of friction, that is the mu, and belt between the belt and the surface. The angle of contact between the belt and the surface, that is beta, what I have explained you in the diagram as described in the equation above. Now in case of V belt, I had shown you the groove from the side view. Now this is what we are taking as the surface of the cylinder, where we will having a V kind of groove here. So the belt which will be fixing here will be V. Now the angle between both the grooves will be angle alpha. In a V belt, the enhanced coefficient of friction takes into account the coefficient of friction between two materials as well as the groove angle. So here the formula changes a bit as e raised to mu s enhanced into beta. Now what is mu s enhanced? It is mu s upon sine of alpha by 2. Alpha here is the angle between both the grooves. Now we'll see some of the theory regarding the same. A V-belt is any belt that fits into a groove on a pulley or surface. For a V-belt to be effective, the belt or cable will need to be in contact with the sides of the groove, but not the base of the groove as shown in the diagram which we have seen right now. With the normal forces of each side, the vertical components must add up the same as what the flat belt would have. But the added horizontal components of the normal forces, which cancel each other out, increase the potential for friction forces. The equation for maximum difference in tensions in V-belt systems is similar to the equation in the flat belt, except we have used enhanced coefficient of friction. Is what I have explained in the previous part of the diagram. That takes into account the increased normal friction forces possible because of the groove. Now moving to the actual experimental setup, how the assembly of experimental. So this is how the apparatus looks like. There is a stand on which a board is placed. On that board there is another ring inside and there is some another kind of pulley arrangement here. This surface on which I am moving my cursor right now is fixed one and the board moves along with the pulley. There are some readings given here, right from 0 degrees to 360 degrees. For you to understand that there are readings, I have included this second diagram, and there are hooks on which another weights can be added. Okay, so for you guys to understand the diagram setup properly, I have included these two figures. Now I will explain you with another diagram that how are we going to perform the practical exactly. So here you can see that there is a complete 360-degree assembly. Now we have to take beta into radians. So we have taken all the values in radians. Now what is this beta? The lap angle, that is the angle of contact between the belt and the pulley. This is the guide pulley which moves with the board. This is graduated disc. Then there is a clamping wheel which holds the inner part of the wheel, and here is the belt. Now the assembly actually includes both flat and V groove together. So it looks like this. Both the parts are closed enough and the flat surface is just adjacent to that of the V groove. And where is this assembly arrangement? It is here on the edge of this clamping wheel. So on the clamping wheel we will put the belt. Now there are two cases for both the belts. For flat belt as well as V belt, we are going to solve by two cases. The first case will be where we will be keeping the beta constant, that we will make sure that there is some angle beta which is fixed. For example, it is 60 degrees, and we will vary the value of T2. Okay, this will be our first part, both for flat belt as well as V belt. In the second case, we will keep this angle T2, this weight T2 constant, and we will keep varying the angle beta. Okay, so this is how we are going to get certain 4 tables. So the first table is the case 1 where we are keeping beta constant. For example, we are taking some value for beta and that we multiply by pi by 180 and we get the value into radians. This is for flat belt, we are calculating beta. We will take some random value of T1. For example, we are taking the value of T1 as 0.5 kg. So converting that into Newton in the second part, and we are also assuming the value of T2 something. So let it be 0.75 equating. Now what is the exact value of T2? How will we decide that? We have to decide it accordingly, where the value of T2 should be exactly when the belt starts sliding over the other side. For example, in this figure you can see that T1 is here and T2 is here. We have fixed some angle beta, let it be 60 degrees. Let T1 be 0.5 degrees as I have taken into reading this example. and then we will put on adding weights on T2, and we will keep adding the weights until unless this belt slides over and starts moving to the right side. Okay, now the second case. This first case has to be done for flat belt as well as for V belt. Similarly, we will take another case where T2 will be constant. That in this figure we will keep the T2 constant and we will keep varying the beta. First we will take 60 degrees, then we will take 75. You can change the values, vary it, anything between the radian values. So there will be two tables accordingly where we will keep T2 constant. This is the first table, that is table number 3. For flat belt, we will take some random value of T1 keeping the radian fixed. Similarly, we will do it for the V belt. So sample calculations here. Using the formula for flat belt and V belt, we will determine the value of mu. Using the above two expressions, you can get the value, and these mu values have to be filled on the right most column of the table. So all the four tables will be having four values of mu. In the result table, you can see average from table 1, from table 2, table 3 and table 4 here. Now we also have to draw graphs. In the results, you also draw graphs. What you have to do for the first case, both for flat belt as well as V belt, the graph will be plotted for T1 versus T2. In the second case, the graph will be plotted for ln of T1 by T2 versus beta. This ln is representing the natural log, and we have to make sure that in the first case it should be a straight line which is passing through the origin, and the slope of the line will be the coefficient of friction. The graph here should be the straight line, the slope of which gives the coefficient of friction for mu for the flat belt. The slope of the line multiplied by sine alpha by 2 gives coefficient of friction for the V belt. So the one which we get straightforward will be the friction for coefficient of friction for flat belt, and when we multiply it with sine of alpha by 2, we get the coefficient of friction for V belt. So these values we will be putting in the values of mu per graph for flat belt as well as for V belt. Thank you so much for listening to the discussion. Before I close down, I would like you to request to please comment in the comment section, so you can mention whether you understood the video or you did not. Thank you again. If there are any kind of queries, you can contact me for the same.